I should. That sounds like 120 decibels. It's not. My watch warns me when it's 80. So I drew my Gaussian surface like this. This is where we left off yesterday. And if you're asking why did I draw it like this? Well, I want to draw a Gaussian surface that makes for the easiest math possible. I mean, that's my goal. So I always want to draw the Gaussian surface in such a way that the math is easy. Now, this Gaussian surface allows for, allows me to look really clearly here and say that, well, if I've got my Gaussian surface inside metal, it's going to be in an area where there is zero electric field. That's pretty good. I like that. And because of the idea that this is, got a uniform electric field, then if I draw my sides so that they are perpendicular to the direction of the electric field, then I should also get a flux of zero. So that's why I've drawn my Gaussian surface like this. And they wanted me to figure out a relationship between sigma 1 and sigma 2. So I wanted to enclose sigma 1 and sigma 2. Thus, I get sigma 1 plus sigma 2, plus sigma has to equal 0. I get that from just looking at the total flux I have here. Now, I can do this a little different, but this is my enclosed charge. I wrote it really fast because we were in a hurry. But I mean, really, the enclosed charge would have to be, because it would involve the area of the Gaussian surface, the part that's not here, the part that looks something like this, that goes back. So the area of this top plate and the area of this top plate. I don't have that, but I'm not going to need it because it's going to be sigma 1 times that area plus sigma 2 times that area plus the sigma of the inner plate times that area equals 0. Right? Because the total flux is 0, which just tells me then that sigma 1 plus sigma 2 is equal to negative sigma. Indicate clearly on the diagram below the Gaussian surface you used. I think we're good with that, right? Any question on where I came up with that? Can you make that face for me, Max? The one where you look exasperated? Oh, okay. Okay, so we'll move on. Develop an expression for the potential difference, V, between the charged sheet and the conducting plates in terms of sigma, A, B, and any fundamental constants. All right. Well, how do you want us to go about doing this one? No ideas at all? But we have so many things we can bring to bear here. So many things that we know. Well, let's look at what we've already found. We have a relationship, right? We could reuse that. We have another relationship that we might be able to use. We have this other thing we could be using. I mean, all of these things I think are going to contribute. And we know this now too. None of that? Bringing any ideas of what we could do? Oh, that makes me a little bit sad. Well, let's see. I need to develop an expression for the potential difference between the charged sheet and the conducting plates. So we're looking at this potential difference right here. I have an electric field this way that I already have an expression for. And the expression I know has something to do with E1 and E2, which equals, it's B over A, right? This is getting to a point of ridiculousness that's almost borders on lunacy. So let's see. Trying to find a good way to communicate this idea to you. We can't have E1 or E2 in our answer, is what I'm gathering. Can we use Gauss's law to figure out what an expression for E1 in terms of sigma 1? I think we can, right? And I think they gave us this as a clue for how we might go about doing it. Meaning, could we have a Gaussian surface? Let me see if I can draw this correctly. But I got to be honest, the interruptions are getting to me a little bit. They're making me feel a little sad. Maybe I can't. I want to touch this. I only want this one though. All right. Can I ungroup it all and duplicate it? All right, there we go. So I'm going to make a slightly smaller one. And move it. Come on. None of this is working for me. Nothing. Now I'm aggravated. So let's just use a different color here. I want to try and place a Gaussian surface, like right there. They suggested Gaussian surface in their prior question, so I'm wondering if we can't kind of use that against them. So if I can't see through that, so there. Something like that. There. Because we have an expression for E2, which is going to be A over B times E1. You guys probably can't see that. We have an expression for E2, which is A over B times E1. Now, knowing that I have this Gaussian surface, one of these surfaces, because of where I placed it, does have flux passing through it and encloses only one set of charge. The charge it encloses is sigma 2 times A. And that has to equal epsilon naught times the flux. And there are, well, there's 4 different surfaces. There's one in the metal. That's got a flux of 0 because the electric field is 0. There's 2 on the sides, but those are perpendicular to the field. And there's this surface right here, which has to have electric field 2 passing through it. So I can write that as electric field 2 times A, the surface of that particular sheet. So cancel the A's out, and I have an expression for electric field 2 in terms of sigma 2A over epsilon naught. I think I could do that for electric field 1 as well. Can't I? I'll move that over so you can see it so I'm not in the way. Won't I get the exact same thing for electric field 1? So electric field 1 would be sigma 1A over epsilon naught. Now, I don't know if you know where I'm kind of going with this, but I'm thinking we should be able to use these to figure out the electric potential. Why do I have A in there? Wouldn't the A have canceled out? And nobody told me that? There. So I have 2 new expressions for E1 and E2 that are based on sigma 1 and sigma 2. I have that the sum of sigma 1 plus sigma 2 equals negative sigma. I think I should be able to use all this to get V. Because ultimately, all I have to do to get V is be able to produce E1 times A or E2 times B. I have to do that without having E1 or E2 in it. So I think we can do this. Don't you? I got all these things, all these pieces here. Just trying to find a way to bring them all together. So I think what I'm going to do is solve these for sigma 1 and sigma 2. That's what I think I'm going to do. Because I know that this equals V and this equals V. So I'm out of space here. So I'm going to move this, make it small, and kind of see if I can mash this together. And I'm just throwing stuff against the wall. I don't really have a plan. This is a weird question. So I'm trying to see if I can find some way to bring it all together to figure out V. But I think the answer is going to be to do this, to say, okay, E1 equals V over A, and E2 equals V over B. Sigma 1 equals E1 times epsilon naught. Sigma 2 equals E2 times epsilon naught. Okay so far? So sigma 1 plus sigma 2 equals negative sigma. I'm allowed to have negative sigma in my answer. So E1 epsilon naught plus E2 epsilon naught equals negative sigma. But E1 is V over A epsilon naught, and E2 is V over B epsilon naught, and that equals negative sigma. I can factor out a V and an epsilon if I want, and I get V epsilon naught equals 1 over A plus 1 over B. You guys can't see that anymore, can you? And that has to equal negative sigma. I think I'm pretty close to the answer here. I'm going to do one thing to make this a little easier. I'm going to combine all that and get B plus A over A times B. That way I can kind of reverse it and multiply it on both sides. So I'm going to get that the voltage equals negative sigma over epsilon naught times AB over B plus A. Now, I didn't have a well-defined plan. I just looked at all the things this problem made me solve for. You know, it made me get this. Okay, can I use that? Well, probably. It made me get these other expressions for electric field. I thought maybe I could mash it all together to bring it together. And that's what I did. I don't think there's anything like equation-wise in physics that would have said, this is how to do this problem. I just looked at the pieces that I had and the things the problem made me do. How many points do you think D was actually worth? I bet it's about 2, maybe 3. So now you see why I wouldn't give this as a test question, though. As the problem goes, it's weird. It's odd. And I hope that you are doing what I am suggesting when I give these FRQs out, that you're sitting for 15 minutes, seeing how far you get in 15 minutes. Now, if you want to go further than that, great, but get an idea for what it's going to be like on the exam. That's what this practice is about. I want you to have perseverance to try and solve the problems. I don't want you spending hours on it, but I think that there's a good mix. You put a solid 15 minutes, see where you get, kind of get an idea for the number of points you're going to get from that, and then maybe finish it out. So you learn something from the experience. That's what these are supposed to be about. Now, if you're one of those people that has like way too much grit or way too much determination and you're spending hours on it, that's probably too much. That's probably too much. All right. I like this question, but I would hate to have seen it on an exam. It's just so weird and non-standard. Mostly because when you start this problem, it looks like it's a capacitor question. And it turns out to really just not be much of a capacitor question. I'd say are there questions, but I know the answer to that. Right now, you're like, ugh, I don't want to ask any questions on this. Yay. Yay. That was funish. Move on a little bit. Are there any outstanding questions on the homework you wish to ask? Yeah, you know the mastering. Okay. Go ahead. No? Okay. We have to tie a few things together that are kind of a mess. So let's bring a few things together real quick. And this is because of the storm and because of me being not particularly organized. So I want to remind you the definition of capacitance, Q over V. We use this to derive capacitance for a parallel plate capacitor, giving us this physical representation for how to build a parallel plate capacitor. When we talk about capacitance, this is one of the more important things to memorize. Where this is like the Ohm's law for capacitors, this is how to construct a capacitor. And unlike the construction of a resistor, the construction of a capacitor has more implications because it relates so much to electric potential, electric field, and energy storage. Because of that, the construction of a capacitor has more value. Now let's see who can win a prize. Cylindrical capacitor, what do we get? No one can win a prize. I'll help you out. It's got a lot of these things in it.
2 pi L over ln B over A.
That's right. It's got a lot of the same features. So look at the features. Now, there should be a kappa here because you can't fill it with the dielectric. Instead of area, we have length, which makes sense. It's how long the capacitor is. Yes, sir. This is the capacitance of a cylindrical capacitor. So it's like a cylinder inside another cylinder. Something like that, like a coaxial cable. A represents the inside radius and B represents the outside radius. But again, it has similar features. I see length on the top instead of area, and this ratio of B to A on the inside. It says the same thing mathematically, that if A and B are very close to each other, then the logarithm is very small and I increase the capacitance. That's the same thing as saying if the two plates are close to each other in a parallel plate capacitor. This comes up very infrequently though. And it's mostly because we don't build them like this. So it's hard to have problems like this. Now, the only one we didn't finish was the spherical capacitor. We got stuck for time. A few people stayed around. Anybody at home remember what it looks like? Many of you stayed.
4 pi epsilon naught AB divided by B minus A.
4 pi kappa epsilon naught. And then it was AB divided by B minus A.
Yeah.
Now, if you don't remember what A and B are, this is for a sphere. So we had the inner sphere and the outer sphere, where this was A and this was B. Notice the same kind of thing. A times B, 4 pi. A times B. It doesn't look like what it is, but it is kind of like the surface area of the sphere. It's not exactly, but for it to be a good capacitor, A needs to be kind of close to B, right? So the distance between the plates is very close. That's why you get more capacitance if A and B are close to each other. And you get this, which is very similar to 4 pi r squared, the area of the sphere. So the big takeaway, what I really want you to understand is that capacitance is always best if the two plates are close to each other, you get the most capacitance. And you're going to get more capacitance if you can spread that charge over a bigger area. That's what increases capacitance. Now, inside capacitors, we tend to focus on the parallel plate, which has its own set of things that tend to show up for the parallel plate capacitor. First, you have an electric field that's related to the potential and the separation distance. That's easy. And because of that, you can have problems about charge inside the plate. We talked about that. And we can combine the capacitance with this force to deal with the force on a parallel plate capacitor, the force between the plates on each plate. And then there's a whole set of problems related just to the idea that you have two infinite sheets or nearly infinite sheets, where the electric field can be related to sigma over 2 epsilon naught. Right, the electric field between an infinite sheet. We kind of see that with our parallel plate capacitors. Now, in addition to all of that, we have systems of capacitors. Systems of capacitors have equivalent capacitance. If they're in parallel, the equivalent capacitance is related to the sum of the inverses. In a series circuit, these capacitors would have the same charge. In a system with parallel capacitors, they will have the same potential. And the equivalent capacitance is equal just to the simple sum. Remind you, it's a 3-step process to figuring out what the capacitance is of a physical set of charges. With step 1, determine Q in terms of the field. Step 2, calculate the potential. From that field. And 3, use C equals Q over V. That's where we found each of these. One final thing about capacitors is putting a dielectric in a capacitor generally increases the capacitance. That's why it's in the numerator of all of those fractions. You put a dielectric in, you increase capacitance, you change the circuit. If the capacitor is connected to electric potential, you manipulate the charge. If the capacitor is not connected to the electric potential, you manipulate the voltage. That's the big summation of all of this. Any questions about this summation? So just trying to bring it all together since it's been kind of straggled out over a couple of, a week, Veterans Day and hurricane days.
Just to clarify, when two capacitors are in series, the charge between them is the same?
Yes.
Okay.
So there's two little tiny details here that are lost. One, I want to talk for just a minute about spherical capacitors. You can't make them, so they're kind of ridiculous. But we got this 4 pi kappa epsilon naught AB over B minus A. It's a little ridiculous. But I want to rewrite this as 4 pi kappa epsilon naught over 1 over B minus 1 over A. Actually, it's the other way around. It's 1 over A minus 1 over B. This part and this are the same. You guys left, but we did that in class for the ones who I just did the video. This has a weird effect. You can take away the exterior plate of a spherical capacitor, and it still has capacitance. And if you look at what this states, if I have a spherical capacitor, then I have an inner plate of radius A and an outer plate of radius B. If B goes to infinity, then this term goes to 0, which leaves us with 4 pi kappa epsilon naught times A by itself, which this is the capacitance of a sphere. A sphere by itself in space is its own capacitor. Now, that doesn't make a lot of sense, except that an isolated sphere then can store energy if it's charged and discharge that energy if necessary. Planets do this, satellites do this. Even though a satellite's not a perfect sphere, satellite in space can be an isolated shell of charge. Any isolated shell of charge that can collect charges or become charged, therefore can discharge and store energy. It's a unique occurrence, but it's not as unique as you seem, because every planet, therefore, has a capacitance. Because every planet that has an atmosphere is collecting charge from the solar rays of the sun. And that means every satellite that goes around the Earth, also a capacitor. We just docked the SpaceX Dragon capsule on the space station. What I've never learned and what I've never looked up is how do they deal with the fact that both of those items are at probably different potentials because they're both charged capacitors. They must have a process for discharging the system ahead of actual contact, or a plan to allow those charges to flow, or maybe they don't. Maybe they just wait till contact and isolate the people inside so they don't become part of the circuit. But you do realize that the two things have to be probably at different potentials when they go to be in contact. I would assume you get close enough, you will eventually draw a spark. We tend to think that sparks in spacecraft are bad. But I guess the spark would be outside the spacecraft. Therefore, it can't ignite anything. Maybe they just don't worry about it. But they got to be at different potentials because there are different capacitances. Anyways, this doesn't come up often, but this is the formula for a spherical isolated capacitor. And I just want to make sure that all the pieces have been displayed in front of you. And the last thing, capacitors do store energy. How much? 1/2 CV squared. Or it can be manipulated two other ways. Do you know what the other ways are? It all involves a little bit of substitution. 1/2 QV. And what's that? Yep. That's it. That is capacitance in a nutshell. All right, tomorrow we're gonna outline something else. It's Thursday and prepare. Friday is gonna be our test on capacitance. I'm going to present to you tonight what I feel is a typical FRQ style question that would be on your test. Not one that's weird, not the one that's trying to trick you, but a typical FRQ that you would expect to see on a test. That's more in line with what we would expect. I want you to spend 15 minutes on it tonight, okay? Tomorrow we're gonna review it, talk about what your test's gonna be like, and that's it. We come back and we just have to do current. So, you guys at home, have a wonderful day. Except for you, Abby, you have to come right back.